We've seen that a magnetic field causes a torque on a current loop. Now let's calculate how much torque using the real definition of torque. So as you know, mechanics is a prerequisite for this class, and it caused a lot of pain and frustration that I don't review a lot of mechanics. But if you're still here, you probably were pretty good with the mechanics. Well, torque is a difficult concept, often at the end of mechanics, so I want to review it just a little bit. Torque, if we describe it as a vector, it's usually the vector tau, and it's equal to R cross F. Now, let's think about what that really means for a second. The easiest way to see it is to open a door. Do you know how a door works? Here is the door to the demonstration closet that is almost always left open in, well, in half the videos. So a door, this big thing, it's on a hinge, and you just push it and it opens, right? That's how a door works, right? Let's draw a door and think about where is the torque, okay? So we're drawing that door looking down, okay? So here is the door. It's a very impressive 100-year-old door. It's got hinges on this side, probably not the original hinges, but this is the hinge, and that is sort of the pivot point. It swings around that hinge, okay? It's also got a knob. The knob actually is kind of this two eagles standing around the key or something like that, but we'll just draw the knob. I won't draw the eagles. So the knob kind of looks like that. Okay. So remember, we're looking down. When you approach the door, you reach out with your hand. Right, here's your head, here's your arm and your legs. You're looking down, we're looking down on you, right? And you push. You push on the door with a force. You push with a force F. That's not a torque. You're pushing with a force. You apply a force. Now, what happens is we know that a torque is when you have a force cause something to rotate about an axis. So the other vector we need is R, and that is from the point, from the axis of rotation out to the point where you apply the force. In this case, the line, the place in the door where you apply the force. So that's R. Right? So if you push from really far from the pivot point, then R is really big. If you push really close, R is really small. So tau is R cross F. The magnitude is just, we want to get the magnitude of tau. It's just R, that distance, times the force, F times sine of theta between them. So if you want to apply the maximum torque, you push at 90 degrees. And that's intuitive, right? You wouldn't go up to a door and to open it, push it like this, all right? You push it straight. You push at 90 degrees to R. If you go pushing at an angle, you get less torque. So this all physically makes sense. The hard part is the direction of the torque, okay? The direction of the torque is not the direction that the thing moves. Let's think about it for a second. It's R cross F. So in this case, R is this way and F is down, right? F is down, R cross F. The torque is into the board. Usually we'd draw it over here, actually where the hinge is, and I just happened to draw the hinge as the torque. I made the hinge look like a little vector going in. That's the torque. So when you're making something rotate by applying a torque, the torque vector is actually perpendicular to the circle that it would make. It's normal to the circle. It's not the direction of the force. It's perpendicular to the radius and to the force, and that's the torque.